Hi and welcome everyone to Maki Academy YouTube channel. As a continuation from the previous example, I'm going to do another example for combined loadings, and remember this is from the revision of mechanical solids part 1. We're going to have a slightly different structure as you can see on the screen right now, and at point A and B for this so-called T-shaped rod, and I'm going to list down all the loads and the dimension for this example. So first of all, let's have a look on the Cartesian chart system of this. Since the question doesn't mention whatsoever the direction, and you need to decide that for yourself. I'm going to take this is my x, y and z for my system, and given to you point loads at two locations at point B, exactly at point B, going towards x direction, which is this way with the magnitude of 3 kilonewton. That is one point load, and the other one is pointing towards z direction, and this is at point C and D. To make it clearer to you, this is another point load pointing that way with a magnitude of 1 kilonewton. We got 2 point loads, and now I'm going to draw the dimension for this example here. The distance here is take as 0.1 meter, and the distance from the point of interest, right? I haven't locate that on the question. This is E that we need to calculate. This is point E. Point E is somewhere along the wall A, and as we all know, for combined loadings, usually they would like to ask at two locations, but for this example, just take at point E, which lies exactly on the middle, or we can say it is on the natural axis of that rod. And the distance for point E towards the end of that rod, T-shaped rod, this is 0.25 meter, and take D as D of the rod as 40 millimeters, that is given, and straight away change it into SI unit. It comes to 0.04 meter. Now we have this question right here, and the question asks to find the stress element. Previously I wrote RVE. RVE stands for representative volumetric element. It is exactly the same thing at point E. So there is the point of interest. We would like to find the stress element. It is just a box with all the stresses involved for this point E, the point of interest. And I would like to mention also for this example, because next we're going to go down into stress transformation. That is the first part of solid mechanics part 2 in the syllabus. We're going to learn how first of all we need to solve for the stress element at that point, and if it is given slanting at an angle, and it is the structure right now, the stress right now need to be shifted, and that is what we call as stress transformation. We need to transform the stress, meaning that we have normal stress and shear stresses, going to convert it into, translate it into, or we going to transform it into the magnitude of the stress is going to be different because we're going to have a set of equations to do so. I'm going to explain to you later, but for this one, this is still under the revision of mechanics of solids, just the second one, the second example. So let's just do that. The question asks, find the stress element at point E. At point E, and I'm going to begin with, of course, the free body diagram, right? Free body diagram for the question, and I would like to take this point here. It is a cross section of that rod, right? And by taking all the Cartesian chart, y, we have y upward. This is z going to out of the paper, and in x, my x going to go this way, right? That is the system that I have, and I'm going to list down all. Begin with this 1 kilonewton. What I'm doing right now is replacing some textbook call this the method of superposition. You superimpose the point loads now at the location that actually this cross section is actually at point E, looking at from I'm just take a section of a point E, and I'm going to list down all the loads that we have, but don't forget we have a rod. We have a distance of 0.1, if you can see on the diagram again, 0.25 from point E to point B. So that going to cause moments. So I'm going to list down that. Now we have look at the 3 kilonewton, 1 kilonewton, the arm of 0.25 meter going to cause a moment on y direction, going to rotate. It's going to rotate. If you can feel that, if you can still recall in chapter torsion, we have right hand rule where your thumb going to show the direction, and your fingers, the rest of the fingers, going to represent the rotation of your moment. In that case, in torsion, there is torsion, your torque. Now, in this moment y, due to 1 kilonewton, going to rotate on y-axis. So if you can feel, I've got to show this diagram again, and looking at 1 kilonewton, going and the distance of 0.25 going to make it rotate on that direction, and I'm going to redraw that in terms of free body diagram right here as this arrow. We have moment y, which is equivalent to 1 kilonewton times by the distance of that 0.25 meter. So and we have another one, 1 kilonewton due to 0.1 meter the distance. That going to cause, right, the rotation as well, but now that is on x-axis. This is moment x equivalent to 1 kilonewton times by 0.1 meter. You're gonna get that the magnitude of the moment due to the force and the arm. In another word, the arm, we got the distance of the location of the point load towards the point that we are interested to calculate. So I hope that there is actually this part right here to identify in three-dimensional. That is the hardest part, according to response from the students. So if you can imagine this is piece of cake to you, it will be going to be simple, the subsequent part of solving the combined loadings. Now let us move to the solution. We have all the stresses, and remember we have the diameter 0.04 meter given in the question, so the radius of this is just half of that. This is 0.002 meter. So I'm going to start with the solution for sigma equivalent to P over A. This is normal stress, and I think we have both normal and bending in this question right here. So yeah, from the previous example, I listed down all the parameters that we have. For example, I, J, right? All the components needed for our solution. It's up to you if there is more you are more comfortable with that. Calculate all the components related to the equations for bending stresses, transfer shear, all of them, right? To calculate that first. Also can in this case I'm going to list down, there are two equations that we need. The other one is the sigma equivalent to my over I. So for this, I need to calculate. It is the same thing. It's just the flow, the sequence is not the same. But all you need to know, all you need to calculate in the first place need to be done. So I'm going to, there is the area. I'm going to calculate that by times by 0.02. Now it becomes easier because we have done that earlier on. This is 0.02 to the power of 2. And this is the value that you're going to get for the area 1257. Of course, the unit is meter square. I'm going to simplify this 1.257 times 10 to the power of -3 meter square. And for my over I, I'm going to need I, right? What is the formula for I? Is pi r to the power of 4 over 4, right? And then solve this pi 0.02 to the power of 4 over 4. Just plug and check the value and hit your calculator. You're gonna get this value 1.257 times 10 to the power of -7, and the unit now is meter to the power of 4. Yep, there is two of the components. For one is for normal stress, the other one I for my bending stresses. I'm going to continue. We haven't solved that, but just to for the sake of revision, I would like to show you. I think it is important to recap this this part also, where I'm going to do it carefully. Would like to show you how we develop because drawing the stress element is not solving the stress at one location. That is not all about it. We need to consider also whether the stress is going to eliminate each other, meaning that if it is in opposite direction, you need to instead of adding them, you first of all you need to calculate how much is the magnitude of the stress. But it is equally important to get them right in terms of whether it rotates opposite. If we have two type of stresses, are they cancelling each other, or are they adds, or going to the magnitude becomes bigger because the rotation or the it adds up. So that is need to be done carefully, and this is the purpose. I would like to draw this diagram right here. This is, again, this is y, right? X, Y, Z. This is X, Y, and Z direction. Hope that is clear. And I'm going to draw these small arrows showing that this is the normal stress due to 3 kilonewton. That is what exactly the 3 kilonewton done on that surface area. If you ask me what that surface area is referring to, is this, right? This is the surface area that we are talking about, and I just want to make it clear that is the and that is why we calculate sigma x is equivalent to p over a, the area. We have done that before. 3 times the power of 10 to the power of 3 Newton, 3 kilonewton divided by the area that we just calculated just now. Now we have to the power of 3 meters square, and you're gonna get that this is the first sigma x in terms of megapascal. This is 2.39 megapascal for the first one. So let's have a look on the other. I'm going to draw exactly the same just to make it super clear. This is the cross section again. I'm going to have this is x, y, and z direction. Now for bending, we have I hope this diagram, this is not it looks like parabolic drawing, but this is right. Probably that is too small, right? I'm going to actually this is another one because I've drawn this on 3-dimension diagram, and notice that we have arrows coming out from the shaft, and these arrows going down the rod. I think it is clearer. I would like to show you is this. We have, for example, neutral axis for this prismatic beam, and what I would like to show is this the maximum of the bending it occurs on the outer skin or outer fiber of the structure. So let's focus on this. This is going downward, this is going away from the board, right? So it shows that there are we have two maximum. Just show for the rod it is much easier because the maximum is always on the outer radius of the rod. So hopefully that is clear to you. What I would like to show is now looking at it is slightly tricky because I hope this diagram here can clarify what we are calculating now. This is moment on y-axis, the moment for bending, right? So is equivalent to force on z direction, which is, see, the force is on times by x. Moment is what we have before, 1 kilonewton times by 0.25 we listed down before, right? I think we did that on the when we draw we begin with the free body diagram. Just want to recap this again clearer here. You can go back to the free body diagram again. We mentioned that then this is just 1 kilonewton, right, times by the distance. So you get 250 Newton meter. That is the unit for the moment. Thus sigma x, right? The distance of we have the moment, just moment times by y divided by the moment of inertia or second moment of area. So just take all the values in here. 250 newtons meter times by y. What is the just is the radius, right? There is hopefully there is no confusion at all over there. This is just and I just put it back in here, 10 to the power of -7 meter to the power of 4. This meter going to cancel, this becomes 2. Now Newton per meter square comes to the unit of Pascal. So just compute that with your calculator. You're going to get sigma x is equivalent to 39.78 megapascal. We have all the two stresses. One is 2.39, right? And another one is 39.78. Are they cancelling each other? Are they x on top of each other? That we need to, if you have a look at point E, the point of interest that we have. So this is what I said. I think that this first and second diagram going to be very important to see that clearly. One is pulling in for E resides on this side right here, guys. So this is point E resides on this side, and both are we can say that the arrow is pulling them, so we need to add them. So I'm going to say this: the total for sigma x is 2.39 plus 39.78 megapascal, and the real value for sigma x is this 42.17 megapascal. So there is a few, we left few things on our free body diagram. We saw for two stresses, and we need to check because there are four. If you can go back to my intro video for this revision, I would like to call it chapter 0 for part 2. We're going to begin with the revision, and I mentioned that we have 4 types of stresses, and there are another 2 before we are able to draw our stress element. Let's check on the shaft again. We have this, right? This is x, y, and z, and we have a moment x time the 1 kilonewton times by the distance of 0.1, and probably that going to cause some stress in terms of shear. I got 2 types of shear, 2 taus if you can recall. One is shear torsion, the other one is transverse shear. So look at point E. We going to have a look on that. This is the moment that we have on x direction, right? Transverse shear. I try to explain this again and again. This is your neutral axis, and the stress profile for transverse shear. It is always parabolic, maximum on neutral axis and 0 at the location of the outer skin. This is opposite with bending. So what do you think at point E? How does because we have a moment x represented by this arrow. This is a moment x that we have. This is moment x. So what happened to because for shear we have 2 equations involved with this type of stress. First of all, the first tau is VQ over IT, and the other one is tau torsion is equivalent to tau times by R divided by J. In this case, we have what happened with transverse shear. Does it going to cause any stress at point E? Transverse shear going to be 0 at the location, the outer skin, and according to the moment that we have right now, moment x, the transverse shear going to, we can say it is equal to 0 because the stresses due to transfer shear doesn't exist, because point E is located at the outer skin. It is not simply because E located at the outer skin of the rod, but remember Q is represented by the equation of A prime times by Y bar prime. So if it is if the area is equivalent to 0, then the whole transfer shear value going to be equal to 0. In this case, and Q, remember, going to be defined whether the point of the point of interest is going to be above or below the natural axis. But in this case, we have rod. It is just a circle, right? And E resides on, I can say that it's on Z direction, on the outer skin on Z direction, on the surface of the rod. And the transfer shear from the definition, it is parabolic, and we can prove that, right? Transfer shear in this case, for this transfer shear equals to 0 on the outer skin, and we left with the torsion for our I think that is the last stress for our calculation. So TR over J, what we need to do right now is to calculate the J, right? J is equivalent to pi r to the power of 4 over 2, or if you don't like using r, the information given in the beginning is the diameter. If you want to use that's also fine. You want to use pi diameter instead of radius, but you need to divide it in with 32. But I'm going to use just this, right? This is pi times by 0.02 to make it consistent with the previous solution. This is then J is equivalent to right over 2 2.513 times to the power 10 to the power of -7. The meter is a meter to the power of 4. So we got our all the elements needed for torsion formula. Now going to finish this off with there's right, tau xy is equivalent to dr over j. T is the now even though we have the 0.1, I say this is moment x, but actually this is exactly the torsion in this case. When it comes to combined loadings chapter, the ability to imagine, because now it is more important to imagine in three-dimensional. Even though I mentioned probably you're going to miss this with the bending by using M bending equation instead, but hopefully now everything is sorted out, and you're going to identify which one is which, right? This is the radius is 0.02. Sorry about that. That is just right, and J 2.513 10 to the power of -7. Go ahead and calculate this, and you're gonna have your shear stress is 7.96, and the unit is of course megapascal. So I mentioned it, probably this part transfer shear is not pretty much clear to you, but having a rod, the Q is going to be 0 according to the definition of Q, the first moment of area, and we haven't done yet. This is last but not least, and you need to come up with this box where our stress element, we're going to list down all the stresses, put it there, x, y as the axis, and this we have a positive the shear stress, and the magnitude is, put it in here. This is tau xy, exactly what we have just calculated before, just now, 7.96 megapascal. And what happened to your, is it in compression or in tension? Identify that, and make sure there are two arrows involved. This is sigma x, right? Sigma x is equivalent to the magnitude of the total. This is 42.17 megapascal. So this is exactly the solution for this. Looking at the question again, right? The question asked to find the stress element. We did that. There is the solution, right? And I would like to reveal. I haven't revealed this in the beginning, because I'm going to use the same example for our. Of course, I'm going to introduce a little bit on stress transformation, but later we're going to see actually at point E, the question can be twisted into, the question might say, if at point E slanting at an angle of 30 degree, now what is the question can ask, now what is normal and shear stress, meaning that sigma and tau, would like to write it down in their own name, right? Normal and shear stresses at point E, where the angle theta now is 30 degree. So, but first of all, looking at this, the very same problem, I'm going to use the same example right here, and you need to compute sigma and tau when we have 30 degree angle. This is a stress transformation is all about. The chapter after that, we're going to learn the strain, stress, wherever we have stress, strain going to comes along. So we're going to cover that as well. But for this example, right, we at the by now you already attempted two examples from combined loadings, and the emphasis I've given in both examples is, I said it is very important for you to imagine in three-dimensional, make sure moment where it's supposed to be. Is it in torsion? Is it torque instead of moment? You need to be able to identify those items, and finally you need to draw this. If you get a correct stress element, this is a stress element at point E, right? The solution for this, if you get it right, everything related to Mohr circle after this, either we're going to attempt it by using stress transformation. We can calculate it. You can calculate by using a set of equation, or you need to use your graph paper. We call it. Previously I mentioned two, right? We have Mohr circle, two types of Mohr circle, right? This is by using just what do we call that? We can say this is one is I don't want to begin with geometrical. This is just graphical. What does it mean by graphical? Is just you can draw. It is pretty much sketch the Mohr circle, but with known values. If you learn engineering drawing, you need to have at least 3 points to make a circle. 1, 2, 3. This is the origin, and you can make a circle, something similar like this. And this is we call it geometrical geometry, right? If I can say that, geometry is by using graph paper, compass, and your protractor to draw. And the second one is just a stress transformation equations. I think right, equations. We're going to explain that in the coming video. So I hope you enjoyed this example. Take it easy and see you on the next lesson.